Hold your hand up in front of you and look at the gap between your fingers and the screen. It looks like nothing is there, just a thin slice of ordinary air, and if you pumped that air away, you might expect to be left with pure emptiness. But that gap, cleared of every atom and every speck of light, is not empty at all. It trembles with energy, and it may quietly be the largest thing in the whole universe, hiding right in front of you. That restless nothing has a name. It is called the quantum vacuum, and over the next couple of hours we will build it up slowly, one plain step at a time, starting from an empty jar on a kitchen table and ending at the edge of a black hole. If you enjoy taking your time with a big idea, consider subscribing, and we will go on together. So here is the simple question we will follow. When you take everything out of a box, what is actually left? Picture a clean glass jar on a kitchen table, with the lid screwed down tight. It looks empty. Hold it up to the light and you see straight through it, and nothing seems to be inside but a little trapped nothing. That nothing is a crowd. The jar is packed with air, and air is a swarm of tiny molecules, mostly nitrogen and oxygen, flying in every direction and bouncing off the glass millions of times a second. You cannot see them because they are far too small and far too fast, but they are there, and their steady drumming on the inside of the jar is what we feel as air pressure. When you say the jar is empty, what you really mean is that it holds nothing you happen to care about. So let us take the crowd out. Imagine a pump fixed to the lid, pulling the molecules away one gulp at a time. The number inside falls, the drumming softens, and the pressure drops towards zero. After enough pumping, the jar holds almost no air at all. This is what most people mean by a vacuum, an empty space with the matter removed, and for a long time that is exactly where the story stopped. But something stubborn remains. Shine a flashlight at the jar, and the light still crosses it as if the emptiness were not there. Bring a magnet close and its pull still reaches through the glass and across the gap. Whatever we have made inside the jar, it is not a true nothing, because things still pass through it, and things still happen in it. Here is the point that will carry the whole story. When you remove everything you can name from a region of space, you are left with something, and that something is the subject of these 2 hours. Physicists call the leftover the vacuum. It is not the everyday emptiness of a cleared room. It is what remains when even the room is gone. The word can trip you up, so it helps to hold it carefully. In ordinary speech, a vacuum means a lack, an absence, a hole where stuff used to be. In physics, the vacuum is a place, the state of a region with the lowest energy it can have, once all the particles are gone. Those two meanings sit close together, and telling them apart is most of the work ahead. Think of it like an empty stage after the actors have left. The everyday view says the stage is now nothing, a blank floor waiting for the next scene. But a stage is still boards and ropes and lights hung in the dark, and the way it is built shapes every play that will ever run on it. The vacuum is the stage of the universe. Take the actors away and the stage remains, quietly shaping what can happen on it. That comparison will only take us so far, and it breaks in an important place. A theatre stage just sits there between shows, still and silent. The vacuum does not sit still. When you look at it closely, with the finest instruments we have, it turns out to be trembling, never quiet, never fully at rest. Finding out why is the heart of this whole climb. For now, keep the jar in mind, cleared of its air, holding what looks like perfect emptiness. We are going to spend the next chapters learning to see inside it. We will start where the real science started, with people who first made a proper vacuum by hand, and who were astonished to find that empty space could push and pull with a force strong enough to stop a team of horses. So the first question is a practical one. Before we ask what empty space is made of, we have to ask how anyone ever managed to make some. The first true vacuum was made with a pool of liquid metal in Italy in the 1640s. The man who made it was Evangelista Torricelli, a mathematician who had worked as Galileo's assistant in the old scientist's final months. When Galileo died, Torricelli inherited both his post in Florence and one of his unsolved puzzles. The puzzle came from well diggers and pump makers. They had long known a strange limit. A suction pump could lift water out of a well, but only so far. Past about 10 meters of height, roughly the height of a 3-story building, the water simply would not rise any higher, no matter how good the pump. Something set a hard ceiling on it, and nobody could say what. The common explanation of the day was that nature abhors a vacuum. The idea, inherited from the ancient Greeks, was that empty space could not exist, so when the pump pulled, the water rushed up to keep any gap from forming. But if nature hated a vacuum that much, why did it give up at 10 meters, rather than lifting the water forever? Torricelli turned the question around. Maybe the water was not being pulled up from above at all. Maybe it was being pushed up from below. The push, he reasoned, came from the weight of the air. We live at the bottom of a deep ocean of air, miles of it stacked over our heads, and all that air has weight and presses down on everything, including the surface of a well. That pressure could drive water up a pipe, but only until the weight of the raised water matched the weight of the air outside. 10 meters of water was simply as much as the air could hold up. It was a beautiful idea, and he found a way to test it. If air pressure set the height, then a heavier liquid should stand in a shorter column. Mercury is about 14 times denser than water, so the air should only be able to hold up a column about 14 times shorter, less than a meter instead of 10. That was a height he could build on a tabletop. So in 1643 he took a glass tube about a meter long, sealed at one end, and filled it to the brim with mercury. He put his thumb over the open end, turned it upside down, and stood it in a dish of more mercury. Then he let go. The mercury in the tube dropped, poured down a little, and stopped. It settled at about 76 centimeters above the dish, close to the height he had predicted, held up by nothing but the pressure of the air on the pool below. And at the top of the tube, above the fallen mercury, something new had opened. A gap. A space that had never held any air, because no air could get in past the mercury seal. It was as close to a piece of genuine emptiness as anyone had ever produced, and it has been called the Torricellian vacuum ever since. He had done 2 remarkable things at once. He had weighed the atmosphere, in effect building the first barometer, since the mercury rose and fell a little from day to day as the weather changed. And he had made a real vacuum on purpose, in a glass tube on a table, where a moment before people had said no vacuum could ever be. Torricelli was quiet about it, sharing the result mostly in letters to friends, and he died only a few years later, still young. But word of the empty space at the top of the tube spread across Europe, and it reached a man in Germany who wanted to make a vacuum far larger than a tube, and to show the whole world how hard empty space could pull. The man was Otto von Guericke, and he was the mayor of the German city of Magdeburg. He was also a tireless tinkerer, and he had built something Torricelli never had, a machine that could pump air out of a sealed container on demand. It was a piston in a cylinder, worked by hand, much like a water pump run in reverse, and with it Guericke could empty a vessel of its air far more thoroughly than anyone before him. He used it to settle arguments about the vacuum by force. If empty space was real, and if the weight of the air was as heavy as Torricelli had claimed, then Guericke could put both ideas on trial in front of a crowd. Around 1654 he arranged a demonstration that people still talk about today. He had 2 large hemispheres made of copper, each one open at the flat face, sized so their rims met in a tight circle. Fitted together with a little grease at the seam, they formed a hollow sphere about half a meter across. There were no latches, no bolts, nothing to hold them shut. They were simply pressed rim to rim, and full of ordinary air they fell apart at the lightest touch. Then Guericke worked his pump and drew the air out from inside. As the air left, the balance of pressure changed. Inside the sphere there was now almost nothing pushing outward. Outside, the full weight of the atmosphere pressed in from every direction, squeezing the 2 halves together with a force no one could see. The hemispheres were now held shut by the air itself. To show how strong that grip was, he harnessed teams of horses to each half, hooked to rings on the copper, and had them pull in opposite directions. The horses strained. The crowd watched. and the empty sphere held. The pull of the atmosphere on those 2 cups of metal was greater than the combined heave of the horses, and the halves would not come apart. Then Guerrica opened a small valve and let the air hiss back inside. The pressure equalized, the invisible grip vanished, and the 2 hemispheres fell apart on their own, dropping into the hands of the men beside them. It was pure theatre, and it was also exact physics. The same air we walk through without a thought had just beaten a line of horses, and the only thing that had changed was whether or not the space inside was empty. The lesson landed hard. Empty space was not a fragile idea that fell apart under scrutiny. You could make it, hold it, and feel its consequences in your arms and in the muscles of a horse. The vacuum was real, and the air around it was heavy, and the 2 facts together explained the pump maker's old ceiling and a great deal more. But notice what this vacuum still was. Guerrica had removed the air, the crowd of molecules, and that was a genuine achievement. What he had left inside the copper sphere was empty of matter in the ordinary sense. If you had asked him what remained in there, he might reasonably have said nothing at all, and for the physics he was doing, that answer worked perfectly. The trouble came from a different direction, and it came from light. Guerrica's empty sphere was dark inside, but it did not have to be. Had he cut a window in the copper, sunlight would have crossed the vacuum without any trouble, just as it crosses the far greater emptiness between the sun and the earth. Light had no problem at all with a space that had no air in it, and that simple fact that light sails happily through the void would soon become one of the deepest puzzles in all of physics. Because if light was a wave, as more and more evidence suggested, then a wave has to be a wave in something, and in an empty space there seemed to be nothing left to wave. Think about the waves you already know, and every one of them is a motion in some material. Ocean waves are the sea itself heaving up and down, so the water is the thing that waves. Sound is a wave too, a pattern of squeezing and stretching that runs through the air, and it needs that air to carry it. Take the air away, and sound has nothing to travel in. Guerrica's own pump could show this. Put a ringing bell inside a jar and pump out the air, and the sound fades to silence while the clapper still visibly strikes. No air, no carrier, no sound. A wave, it seemed, was always a disturbance moving through a medium, and without the medium there was no wave at all. Now, bring in light. By the early 1800s, careful experiments had convinced most physicists that light was a wave as well. The clearest of these came from Thomas Young in England, who in 1801 shone light through a pair of narrow slits and watched it land on a screen beyond. Instead of 2 bright lines, he saw a row of bright and dark bands. Those bands are what waves do when they overlap, adding up where they rise together and cancelling where one rises as the other falls. Water waves make the same pattern. Sound waves make it too. Light made it, so light was a wave. That result was a triumph, and it settled a long argument in favour of the wave picture. But it also opened a crack that would take a century to close. If light is a wave, and if every wave must be a wave in something, then what is the something that light waves in? The question has real bite, because light does not need air. Sunlight reaches us across the emptiness of space, crossing tens of millions of miles where there is no atmosphere to carry anything. Starlight comes from far greater distances still, through a void so complete that Guerrica's best vacuum would look crowded beside it. Whatever light is waving in, it fills that emptiness all the way from the stars to your eye. So physicists faced a clean choice, and neither branch was comfortable. Perhaps light was not a wave after all, despite Young's bands, and was instead a stream of tiny particles that needed no medium. Or perhaps light really was a wave, and empty space was not empty in the way it looked, but was filled everywhere with some unseen material that light could ripple through. The wave evidence kept piling up, and it was very hard to argue with. Interference, the bending of a light around edges, the way it spread through a slit, all of it fit a wave and fought against a simple stream of particles. So most physicists took the second branch. They decided that space was not truly empty. There had to be a medium hiding in the void, thin enough to escape every test, yet real enough to hold up the light of every star in the sky. You can feel the pressure that led them there. They were not being foolish or stubborn. They were following the best evidence they had, and the evidence said light was a wave, and everything they knew about waves said a wave needs a medium. Given those two facts, an invisible medium filling all of space was not a wild guess. It was almost forced on them. So they gave it a name, and they gave it properties, and they set out to find it. They called it the luminiferous ether, the light-bearing ether, and for most of the 1800s it was taken as one of the basic furnishings of reality. It was the first great attempt to say what empty space is secretly made of, and understanding why it was so appealing and why it finally failed is the next step in the climb. The ether had to be a strange material, and physicists knew it from the start. To carry light, it had to fill every gap in the universe, seeping into the space between the stars and into the space between the atoms of a stone. And it had to carry light at an enormous speed, about 300,000 kilometers every second, which put hard demands on what kind of stuff it could be. Here is the difficulty. Waves that move fast through a material need that material to be stiff. In a solid, the more rigid it is, the quicker a wave runs through it, which is why a sound wave travels faster through steel than through air. For light to move as fast as it does, the ether would have to be stiffer than steel, more rigid than any solid we know. Yet the planets swing through it year after year without slowing in the slightest. So the ether had to be firmer than a diamond and thinner than a breath at the same time, a solid you could walk through without noticing. Stranger still was the kind of wave light turned out to be. Some waves push back and forth along their direction of travel, the way sound compresses the air ahead of it. Others wave from side to side across the line of motion, the way a rope shakes when you flick one end. Light waves sideways, and a sideways wave is exactly the kind that only a solid can carry. Liquids and gases cannot support it, so the ether was pushed even further toward being a solid, an impossibly rigid jelly filling the whole of space, through which the Earth sailed without a whisper of resistance. For all its oddness, the ether soon gained powerful support from a Scottish physicist named James Clerk Maxwell. In the 1860s, Maxwell wrote down a set of equations that tied together electricity and magnetism, two forces that had always seemed separate. His equations described how a changing electric field makes a magnetic field, and how a changing magnetic field makes an electric one. Together, he showed, they could feed each other and travel as a wave. Then came the moment that stunned everyone, including Maxwell. He worked out how fast such a wave would move, using only numbers measured in laboratories from magnets and electric currents. The speed that fell out of his equations was the speed of light. Light, he realized, was not something separate from electricity and magnetism. Light was an electromagnetic wave, a ripple of these two fields moving together through space. This tied the ether even more tightly into physics. If light was a wave of the electric and magnetic fields, then the ether was the thing those fields lived in, the material whose trembling we see as light and feel as magnetism. It was no longer just a prop invented to save the wave theory. It was the seat of one of the great forces of nature, the medium in which electricity and magnetism did their work. By the late 1800s, the ether was nearly everywhere in physics. It was in the textbooks and the lectures and the leading theories. Serious people spent careers working out its properties, trying to picture its swirling structure, treating it as solid fact. Empty space, in this view, was not empty in the least. It was filled to the brim with a rigid, invisible, all-pervading sea, and everything that crossed the void, every beam of sunlight and every pull of a magnet was really a motion in that sea. There was only one problem, and it was a serious one. If the Earth was moving through a fixed ether, like a ship sailing through still water, then someone standing on the Earth ought to feel a kind of wind, an ether wind blowing past. Light sent along that wind should travel at a slightly different speed than light sent across it. The effect would be tiny, but two Americans built an instrument delicate enough to catch it, and what they found, or rather what they failed to find, would bring the whole grand structure down. The two Americans were Albert Michelson and Edward Morley, and in 1887, in Cleveland, they built one of the most careful experiments in the history of science. Michelson had a gift for measuring light with almost unbelievable precision, and he had designed an instrument to catch the faint ether wind that the Earth's motion was supposed to stir up. The instrument was a kind of light race. A single beam of light was split into two, sent off at right angles down two arms of equal length, bounced back by mirrors, and brought together again at the end. When two light waves recombine, they interfere, making that same pattern of bright and dark bands Thomas Young had seen. The exact position of the bands depends very sensitively on how long each beam took to make its trip. Here was the idea. If the Earth was rushing through the ether, then light sent along the direction of that motion should take a slightly different time than light sent across it, just as a swimmer takes a different time going up and down a river than crossing it and back. The difference would be minute, but Michelson's instrument was sensitive enough to see it. As they turned the whole apparatus around, swapping which arm pointed into the ether wind, the band should shift. They took extraordinary care. The whole device floated in a pool of mercury so it could turn smoothly without jarring, resting on a heavy stone slab to keep it steady. They made their readings at different times of day and different times of year, so the Earth's own motion around the Sun would point the arms every possible way through the supposed ether. Then they watched the bands and waited for the shift. The shift did not come. However they turned the instrument, whatever the hour or the season, the bands stayed where they were. The light took the same time to travel along both arms in every direction, as if there were no ether wind at all. The Earth was moving, of that there was no doubt. Yet the light behaved as though the Earth stood perfectly still in the sea it was supposed to be ploughing through. This is what physicists call a null result, an experiment that finds nothing where it expected something, and it is one of the most important nulls ever recorded. Michelson himself was disappointed at first, feeling he had failed to detect the effect he was hunting. But the failure was the discovery. The ether wind that should have been there was simply not there, and no amount of refining the experiment could conjure it up. For a while, physicists tried to save the ether anyway. Perhaps the Earth dragged a layer of ether along with it, so there was no wind near the ground. Perhaps solid objects shrank slightly in the direction they moved, by just the right amount to hide the effect. That last idea, worked out by George Fitzgerald and Hendrik Lorentz, was clever and even partly correct in its mathematics, but each patch made the ether stranger and harder to believe, a medium that could not be detected no matter how you tried. Something was clearly wrong at the foundations. The wave evidence for light was still overwhelming, so light was still a wave. Yet the medium that light was supposed to wave in refused to reveal itself by even the smallest sign. The speed of light came out the same in every direction, no matter how the observer moved, which made no sense if that speed was measured against a fixed c. The answer, when it came, did not repair the ether. It removed it. A young clerk in a Swiss patent office looked at the same speed of light that had confounded everyone, took it not as a puzzle to explain away but as a law of nature to build on, and in doing so changed what empty space itself was allowed to be. The clerk was Albert Einstein, and in 1905 he was 26 years old, working at the patent office in Bern, doing physics in his spare hours. That year he published a paper on the motion of light and moving bodies that would quietly retire the ether forever. It carried the ideas we now call special relativity. Einstein started from a bold refusal. Instead of asking why no one could detect the ether wind, he decided to stop trying. He took the stubborn fact head on. The speed of light in empty space is the same for everyone, no matter how they are moving and no matter how the light was sent. This was not a puzzle to be explained by shrinking rulers or dragged ether. It was a basic law, as solid as any in physics, and he chose to build on it rather than around it. From that one law, strange and beautiful consequences follow. If everyone measures light at the same speed, then two people moving differently cannot agree on distances and times in the old comfortable way. A moving clock runs slow. A moving ruler is short. Two events that look simultaneous to you may happen at different moments to someone gliding past. Space and time, which had always been treated as a fixed and separate stage, turned out to bend and stretch, depending on how you move through them. This sounds far removed from an empty jar, but it strikes right at the heart of the matter. The whole reason for the ether was to give light a medium and a fixed frame to move against. Einstein showed that light needs no such frame. Its speed is not measured against any invisible sea. It is simply the same for all, and once you accept that, the ether has no work left to do. A medium you cannot detect, that has no effect on anything, that exists only to carry a wave which turns out not to need carrying, is a medium you can let go. So Einstein let it go. In his physics, there is no luminiferous ether. Light travels through truly empty space, needing nothing to wave in, and the old picture of a rigid sea filling the universe simply vanished from serious science. Empty space became empty again, in a cleaner and stranger sense than before. It was not a material. It was a stage that carried no wind of its own. It would be easy to think the story ends here, with the void swept clean of its imaginary filler. And in one sense it does. The ether never came back. No experiment has ever found it, and no physicist today looks for it. On this point, Einstein was completely right, and the emptiness of space, freed of that invisible jelly, felt genuinely empty for the first time in a century. But notice what Einstein had actually removed. He had taken away the mechanical medium, the stiff sea that light was supposed to ripple through. He had not said that space contains nothing. He had said only that light does not need a material carrier, and that its speed is a law unto itself. The question of what is really present in an empty region of space, once the ether is gone, was still wide open. And there were already hints that the answer was not simply nothing. Maxwell's electric and magnetic fields did not disappear when the ether did. They were still there, spread through space, still able to hold energy and to carry light. Einstein had removed the sea, but the fields remained, quietly filling the very emptiness he had swept clean. What those fields are, and how they refill the void, is where the story turns next, and it is where the vacuum starts to come alive. To see what stayed behind, we have to go back to an English bookbinder's apprentice named Michael Faraday. Faraday had little formal schooling and almost no mathematics, but he had a genius for picturing how nature works. When he studied magnets and electric charges, he did not think of forces reaching invisibly across empty gaps. He imagined lines threading through the space around them, filling it, a kind of tension spread through the room. You have seen his picture without knowing it. Scatter iron filings on a card and hold a magnet beneath, and the filings line up in looping curves, tracing arcs from one pole to the other. Faraday took those curves seriously. To him, they were not a trick of the filings. They were a map of something genuinely present in the space around the magnet, a condition of that space, there whether or not any filings revealed it. He called it a field. A field is a simple and strange idea at once. It means that space itself carries a value at every point, a strength and a direction, ready to push on anything that comes along. Near a magnet, every point of the surrounding space has a magnetic value, telling a compass needle which way to turn if you place it there. Near an electric charge, every point has an electric value, ready to shove another charge. The field is not the magnet and not the charge. It is the state of the space between them. Maxwell took Faraday's pictures and gave them exact equations, and in doing so he made the field the true actor in the story. Light, remember, turned out to be a wave of the electric and magnetic fields moving together. And here is the key point that outlived the ether. A light wave, once it is launched, carries its own fields with it. A changing electric field makes a magnetic one, which changes and makes an electric one. On and on, the wave holding itself up as it flies. It needs no medium underneath. The field is not a motion in some other stuff. The field is the stuff. So when Einstein swept the ether away, The fields did not go with it. They could not. They carried energy. They carried momentum. They pushed on real charges and did real work. A beam of sunlight crossing empty space is a ripple in the electromagnetic field, and that ripple is as real as the sun. The field is a genuine occupant of the void, not a ghost, and it remains even where no matter is present at all. This is the first honest answer to our question about the empty jar. Pump out every molecule, and the electromagnetic field is still there, threaded through the space, ready to carry any light that passes and to feel any charge that enters. Empty space is not a blank. It is filled, everywhere and always, with fields. But now a careful person will push back, and the push is fair. Yes, the field can be present in empty space, but only when something has stirred it up. A magnet nearby, a passing light wave, a distant charge. Take all of those away, quiet everything down, and the field should settle to zero, flat and still and carrying nothing. In the physics of Faraday and Maxwell, a truly undisturbed field is simply switched off. Its lowest state is perfect stillness, a value of zero at every point, which looks a great deal like nothing after all. And for a while that was the expectation. The vacuum was the state where every field had relaxed to zero, calm and empty, holding no energy and doing nothing. It was a reasonable picture, and it fit everything known at the time. Then came the quantum, and the discovery that a field, like everything else in the small world, is never allowed to be perfectly still. The rule that forbids perfect stillness came from a young German physicist named Werner Heisenberg, who in 1927 wrote down what we now call the uncertainty principle. It is one of the deepest facts about the small world, and it will run underneath everything from here on, so it is worth taking slowly. Start with an ordinary particle, say a single electron. In everyday thinking, that electron has a definite place and a definite motion at every instant. It is here, moving this fast in this direction, and if we only had sharp enough eyes, we could read off both at once. The uncertainty principle says that this picture is wrong at the root. A particle cannot have both a perfectly definite position and a perfectly definite motion at the same time. The two are linked, and pinning one down loosens the other. It is not a limit of our instruments. It is a limit built into nature. The more precisely an electron's position is fixed, the more wildly uncertain its motion becomes, and the more precisely its motion is fixed, the more its position blurs out. You can trade one for the other, but you can never drive both uncertainties to zero together. There is a floor set by a tiny number called Planck's constant, below which the product of the two cannot go. You can feel the strangeness with a small thought experiment. Suppose you want an electron to sit perfectly still in one exact spot. To hold it in that exact spot, you must fix its position completely. But the moment you do, its motion becomes utterly undefined, which means it could be moving at almost any speed. An electron pinned to a point is not calm. It is frantic. The very act of confining it forces a wild, unavoidable jitter into its motion. Perfect stillness, it turns out, is not allowed. Now carry this rule over to a field, because the same logic applies. Maxwell's electromagnetic field has, at each point, a value and also a rate of change, how strong it is and how fast it is shifting. These two play the same paired roles that position and motion play for a particle, and the uncertainty principle binds them in just the same way. You cannot have the field's value and its rate of change both be exactly zero at once, any more than you can pin an electron's place and motion together. This is the hinge of the whole story, so let it land. In the old picture, the empty vacuum was the state where every field relaxed to a value of zero and stayed there, flat and motionless. The uncertainty principle says that state is impossible. A field frozen at exactly zero, with exactly zero rate of change, would have both of its paired quantities perfectly fixed at once, and nature forbids that. The field is not allowed to be perfectly still and perfectly flat. It must always retain a little unavoidable tremble. So the calm, switched-off vacuum of Faraday and Maxwell cannot exist. Even with every particle removed, every magnet carried away, every light wave gone, the electromagnetic field cannot settle into flat stillness. It has to keep a residual shiver, a lowest possible level of activity that can never be removed, because removing it would break the deepest rule of the quantum world. That leftover shiver has a name, and it is the first real occupant we have found inside the empty jar. It is called zero-point motion, the motion that remains at the very bottom, when everything that can be taken away has been taken away. It is a small effect, easy to ignore in daily life, but it is always there, in every field, at every point in space, and it never stops. To see what it means, we can look at what it does to matter, cooled as close to perfect stillness as nature allows, at the coldest temperatures ever reached. To feel what the leftover tremble means, we have to talk about cold, real cold, far below anything you have ever touched. Temperature is really a measure of motion. When something is hot, its atoms are jiggling fast. When it cools, they slow down. So it seems natural to imagine a lowest possible temperature, a point where all the jiggling stops and everything holds perfectly still. That point is called absolute zero, and it sits at about minus 273 degrees on the Celsius scale. In the old physics, absolute zero was exactly that, the great stillness, the temperature at which all motion ceases. Cool a substance all the way down and every atom would freeze in place, silent and fixed. It was the coldest, calmest state anything could reach. The uncertainty principle will not permit it. An atom frozen perfectly in place would have both a fixed position and a fixed, zero motion, and we have just seen that nature forbids that pairing. So even at absolute zero, when every last scrap of heat has been drawn out, the atoms cannot come fully to rest. They keep a small, irreducible jiggle, a motion that has nothing to do with temperature and everything to do with the quantum rule. This is the zero-point motion, and the energy it carries is called zero-point energy, the energy that stays when all the heat is gone. For a long time, this could sound like a technicality, a small correction with no visible effect. But nature shows it to us plainly, in a substance called helium. Helium is the second lightest element, and its atoms are light and only weakly drawn to one another. Cool almost anything else toward absolute zero, and it freezes solid, its atoms locking into a rigid crystal. Helium refuses. Cooled all the way down, at ordinary pressure, helium stays liquid. It will not freeze no matter how cold you make it. The reason is the zero-point motion. To become a solid, helium's atoms would have to settle into fixed places in a crystal, each one held tightly in its spot. But holding an atom in a fixed spot sharpens its position, and the uncertainty principle answers by giving it a wild jitter of motion. For helium, whose atoms are so light and so loosely bound, that unavoidable jitter is strong enough to shake the crystal apart before it can form. The zero-point motion literally keeps the liquid from freezing. Only by squeezing helium under great pressure can you force it to solidify at all. So here is a fact you can point to. There is a liquid on Earth that stays liquid at the coldest temperature that exists, and the reason is the tremble that the quantum vacuum insists upon. The leftover motion is not a bookkeeping trick. It changes what matter does, in a way careful experimenters have measured many times over, and if the atoms cannot hold still, the fields between them cannot either. Every field carries its own zero-point energy, its own lowest level of unavoidable activity, spread through all of space. The electromagnetic field has it. So does every other field we will meet. Empty space, cooled to absolute zero and swept clean of every particle, still hums with this floor of energy that can never be removed. That leaves us with a genuinely new picture of the void. It is not a flat calm. It is a sea of restless fields, each one shivering at its lowest allowed level, filling every point of what we used to call empty. To understand that sea properly, and to see how particles themselves rise out of it, we need the theory that grew up to describe fields in a quantum world. It treats every particle in the universe, and the empty space around them, as ripples in fields that stretch everywhere. The theory is called quantum field theory, and it is the deepest picture of matter we have. It grew up across the 1920s, 30s and 40s, built by many hands, and it answers a question that the older physics left dangling. If light is a ripple in the electromagnetic field, then what is an electron? What is any particle of matter? The answer it gives is both simple and hard to swallow. Every particle is a ripple in a field too. Hold the idea gently, because it overturns the usual way of thinking. We tend to picture the world as built from tiny hard grains, little balls we call electrons and quarks, moving through empty space. Quantum field theory turns that inside out. It says the fields come first. Spread through all of space, underneath everything, there is a field for each kind of particle. There is an electron field, filling the universe. There is a field for every type of quark. The photon, the particle of light, is a ripple in the electromagnetic field we already know. A particle, in this view, is a lump of energy in its field, a knot of vibration in something that stretches everywhere. When we say an electron is here, we mean the electron field is excited at this spot, humming with a unit of energy that stays together and moves along like a travelling ripple. Create an electron, and you have plucked the electron field into life at some point. Destroy it, and the field settles back down. The particle is not a separate thing sitting on top of the field. The particle is what the field is doing. An everyday comparison helps, so long as we know where it fails. Think of the surface of a still pond. Tap it, and a ripple spreads outward, a clear moving bump you can point to and follow. The ripple is real, it carries energy, it can push a floating leaf. Yet the ripple is not a separate object added to the pond. It is the pond itself moving. In the same way, a particle is not an object added to its field. It is the field moving in a particular way. Where the pond comparison breaks is important. A water ripple can be any size at all, as gentle or as large as you please. The ripples in a quantum field cannot. They come only in whole units, fixed lumps of energy, never half a lump. You can have one electron or two, one photon or three, but never 2/3 of one. This is the quantum in quantum field theory, the rule that the field's ripples come in indivisible packets. Each packet is a particle, and every electron in the universe is identical to every other, because each is the same kind of packet in the same single field. This picture ties the whole world together in a way loose grains never could. Why is every electron exactly alike, with precisely the same mass and charge? Because they are not separate objects that happen to match. They are all ripples in one field, so of course they are identical, the way every wave on one pond obeys the same rules of that water. The sameness of particles, long a mystery, falls out naturally once the field comes first. And now the empty jar looks different yet again. If particles are ripples in fields, and if the fields are everywhere, then the vacuum is simply the state of all those fields when none of them is rippling into a particle. It is the fields at rest, or as close to rest as the uncertainty principle allows. Not nothing, but the quiet, unexcited condition of the fields that fill all of space. To understand the vacuum, then, we have to understand exactly what it means for a field to be at its lowest, calmest setting, the ground floor beneath every particle. Physicists have a precise name for the calmest setting of all the fields. They call it the ground state, and the vacuum is exactly that, the ground state of the whole system of fields that make up the world. The word ground is well chosen. It does not mean nothing. It means the bottom, the floor, the lowest place you can stand. Picture a ladder standing against a wall. The rungs are the different amounts of energy a field can hold. Add a particle, and you climb a rung. Add another, and you climb higher. Each ripple in the field, each unit of excitation, lifts the field up one step. The vacuum is what you have when you climb all the way back down to the lowest rung there is. It is not the absence of a ladder. It is standing on its bottom step with nowhere lower to go. That bottom step is the key. In the old picture, the lowest state was true zero, a field flat and empty holding no energy at all. But the uncertainty principle raised the floor. The lowest rung is not at zero. It sits a little above, at the level of the 0-point energy we met earlier, the tremble that can never be removed. So the vacuum is the ground state, and the ground state still hums. You have climbed as low as nature allows, and you are still not at nothing. This reframes the whole question of empty space. When we ask what is left after we remove everything, we are really asking what the ground state of the fields looks like. And the answer is that the ground state is a real, definite physical condition with its own energy, its own structure, its own behaviour. It is the quiet baseline of the universe, the state the fields fall back to when nothing is exciting them. Emptiness is not the lack of a state. It is a particular state, the lowest one. There is something freeing in seeing it this way. We stop thinking of the vacuum as an absence, a hole, a nothing that happens to be there. We start thinking of it as the foundation, the floor on which everything else is built. Every particle in your body is a step up from this floor. Every beam of light is a ripple above it. Take all those steps away and you do not reach non-existence. You reach the ground, the state the universe rests on when it is doing nothing at all. And a foundation has properties. The ground floor of a building is not just empty space between the basement and the first story. It has a structure that holds up everything above it, and if that structure were different, the whole building would stand differently. The vacuum is like that. Its properties are woven into how every particle behaves, how every force acts, how the universe is put together. Change the vacuum, and you change the world built on it. This is why physicists care so much about a thing that looks like nothing. The vacuum is where the laws of physics show their hand most plainly, because there is nothing else in the way. Study the empty ground state carefully enough, and you learn the deep rules that govern everything, the settings of the fields that particles merely decorate. So we have arrived at a solid, honest picture. The vacuum is the ground state of all the fields, the lowest rung, humming faintly with 0-point energy that can never be stilled. It is a real state, not an absence, but we have described it so far as calm, as quiet, as the peaceful floor beneath the noise. That calm is not the whole truth. Look closely at the ground state, closely enough to see its finest grain, and the quiet floor turns out to be seething with a strange and constant activity, a flicker that never stops. The flicker comes from the same uncertainty principle, seen from a slightly different angle. We met it first as a link between position and motion. There is another version that links energy and time. It says that over a very short span of time, the energy of a system cannot be perfectly fixed. The briefer the moment, the more the energy is allowed to wander. Nature keeps loose books over short intervals, and only settles them exactly over long ones. This has a startling consequence for the vacuum. For a fleeting instant, a patch of empty space can hold more energy than its calm ground state should allow, because over so short a time the energy is not pinned down, and energy, as Einstein taught, can turn into matter. So in that brief flush of borrowed energy, particles can appear out of the empty field, flicker into being, and vanish again before the books are balanced. They come in pairs, a particle and its antiparticle, born together and gone together, lasting only a sliver of a moment. These are called virtual particles, and the word virtual matters. They're not ordinary particles you could catch in a detector. They appear and disappear too quickly for that, living on borrowed energy that must be repaid almost at once. A pair of them winks into existence, lives for a flash, and annihilates back into the field it came from. Then another pair, somewhere else, does the same. All through the vacuum, everywhere, at every instant, this quiet churning goes on, a constant boil of fleeting particles rising and falling back. You have to be careful here, because it is easy to say too much. The virtual particles are not tiny objects really sitting in empty space, waiting to be seen. They are a way of describing the restlessness of the quantum fields, the fluctuations that the uncertainty principle demands. When physicists calculate what the vacuum does, these flickering pairs appear in the mathematics as a bookkeeping of that restlessness. Whether you picture them as real little things or as a figure of speech, the underlying fact is solid. The vacuum fluctuates. It is never truly still. An image can help if we hold it loosely. Think of the surface of a pot of water just before it boils, when tiny bubbles keep forming and collapsing across the whole surface, too small and quick to break free. The water looks smooth from across the room, but up close it is trembling with these fleeting bubbles. The vacuum is a little like that, calm at a distance, seething when you look closely, alive with pairs that form and vanish faster than any clock can follow. Where the boiling water image fails is in the source. Water bubbles because it is hot, because heat drives the motion. The vacuum's flicker has nothing to do with heat. Cool the vacuum to absolute zero, take away every last trace of warmth, and the fluctuations carry on exactly the same. They do not come from temperature. They come from the uncertainty principle itself, the deep rule that forbids any field from ever being perfectly still. This is a colder, stranger restlessness than boiling, one that no amount of chilling can quiet. So the peaceful ground floor is not peaceful after all, not at the finest grain. It is a froth of fleeting particles, a field that shivers and boils in place, empty of any lasting matter yet never once at rest. This is the quantum vacuum in full, and it is about as far from the old idea of empty space as we have come. There is a fair doubt to raise here. These virtual particles vanish as fast as they appear, and no detector can ever catch one in the act. A restlessness you can never see directly might seem like a story physicists tell themselves and nothing more. But the flicker leaves marks. It reaches into the real world and changes things we can measure, and the first person to glimpse its hidden structure did so years before anyone spoke of fluctuations at all. The person was Paul Dirac, an English physicist known for his silence and his almost unearthly gift for mathematics. In 1928, he set out to write an equation for the electron that would honour both the quantum world and Einstein's relativity at once. He succeeded, and the equation he found was so elegant that it seemed to know more physics than he had put into it. But it came with a puzzle that would not go away. The equation had solutions Dirac did not expect and did not want. Alongside the ordinary electrons with their ordinary positive energy, it described states with negative energy, electrons that would carry less than nothing. This made no physical sense on its face. Worse, if such states existed, every ordinary electron should tumble down into them, spilling out energy as it fell, and all the matter in the universe should collapse in an instant. Plainly, it does not. So the negative energy states had to be dealt with somehow. Dirac's answer, in 1930, was one of the strangest and boldest ideas in physics. Suppose, he said, that the negative energy states are not empty. Suppose they are all already filled, every last one, by an unseen ocean of electrons spread through the whole of space. Because they are completely full, and because two electrons cannot share a state, an ordinary electron has nowhere to fall. The sea blocks the way. What we call empty space is, in this picture, brim full of these hidden electrons, so uniform and so complete that we never notice them, the way a fish might never notice the water it has always swum in. This was the Dirac Sea, and it turned the vacuum into something with hidden structure, a filled ocean beneath the visible world. On its own, that might have stayed a curious fix. But Dirac saw further. If the sea is full, what happens if you lift one electron out of it? You would leave behind a gap, a hole where a negative charge used to be. And a missing negative charge, Dirac realized, would behave exactly like a present positive one. The hole would look like a particle, with the same mass as an electron but the opposite charge. He had predicted antimatter, a twin of the electron, identical in mass, opposite in charge, arising as a hole in the hidden sea of the vacuum. At first, Dirac hesitated, wondering if the hole might somehow be the proton, but the masses did not match. The hole had to be something new, a positive electron that no one had ever seen. Then, in 1932, an American physicist named Carl Anderson found it. Studying cosmic rays with a cloud chamber, he saw a track that curved the way an electron's would, but bent the opposite way in the magnetic field as a positive charge must. It was a particle with the electron's mass and a positive charge, exactly the twin Dirac's equation had called for. Anderson named it the positron. An antimatter passed from a strange idea in an equation to a real thing captured on film. The modern view has since moved past the literal sea. In today's quantum field theory, we do not picture an infinite ocean of hidden electrons. Antimatter arises more cleanly, as another kind of ripple in the fields, and the negative energy states are handled without filling them up. But Dirac's sea was the first serious hint of what the vacuum turned out to be. It was the first time anyone suggested that empty space has a deep structure, that what looks like nothing is really a full and active state, and that its hidden character could reach out and produce real particles you could find in a laboratory. Dirac had shown that the vacuum has depths. The next surprise showed that those depths reach all the way inside the atom, nudging the light we see by an amount no one had predicted. The proof came from the simplest atom there is, hydrogen, a single electron bound to a single proton. By the 1940s, physicists thought they understood it thoroughly. Dirac's equation predicted the energy levels of hydrogen, the specific rungs the electron can occupy, with great precision. Two of those levels, in particular, were supposed to sit at exactly the same energy, perfectly matched by the theory. In 1947, an American physicist named Willis Lamb decided to check. He had spent the war years working on microwave technology for radar, and he turned those same techniques onto the hydrogen atom, probing its levels with microwaves far more finely than anyone had before. If the two levels truly had the same energy, his experiment would find no gap between them. He found a gap. It was a tiny difference, but it was unmistakably there. The two levels that Dirac's equation had placed at the same energy were in fact slightly apart, split by a small amount that the best theory of the day could not explain. This difference is now called the Lamb shift, and its discovery sent a jolt through physics. Something was nudging the electron's energy, something the existing equations had left out entirely. That something was the vacuum. The electron in a hydrogen atom does not sit in truly empty space. It sits in the quantum vacuum, in the midst of all those fluctuating fields and their flickering virtual particles. As the electron moves around the proton, it is constantly jostled by the trembling of the electromagnetic field around it, buffeted by the vacuum's ceaseless restlessness. That jostling shifts its energy, ever so slightly, and shifts the two levels by different amounts, so that a gap opens where the older theory saw none. The Lamb shift is the vacuum's fluctuations, reaching inside an atom and leaving a fingerprint we can measure. This was the moment the restless vacuum stopped being a philosophical worry and became hard experimental fact. Lamb had measured to real precision an effect that only made sense if empty space was seething with activity. The fluctuations were not a way of speaking. They were doing something in the most studied atom in physics by an amount you could read off an instrument. The result landed at a famous gathering in 1947, a small meeting of leading physicists on Shelter Island, off the coast of New York. Lamb's measurement was the news of the conference, and it lit a fire under the theorists in the room. They had a precise number now, a real effect crying out for explanation, and it drove them to finish a theory that could account for it. That theory is called quantum electrodynamics, the quantum theory of light and electrons, and it was brought to full power in the years right after Shelter Island by Richard Feynman and Julian Schwinger in the United States and Shinichiro Tomonaga in Japan, working separately toward the same end. Their theory could calculate the Lamb shift and match Lamb's measurement once it learned to include the electron's constant conversation with the vacuum around it. quantum electrodynamics went on to become the most precisely tested theory in all of science, agreeing with experiment to a staggering number of decimal places, and its success rests on taking the restless vacuum completely seriously. So the vacuum had now shown its hand inside the atom. Its fluctuations moved the energy levels of hydrogen by a measurable amount, and the theory that captured this became a triumph of physics. Yet all of this was still, in a sense, indirect, an effect read off the light of an atom. The next step made the vacuum push on solid objects directly, close two ordinary metal plates with a force from empty space, and let physicists feel the void with a machine. The idea came from a Dutch physicist named Hendrik Casimir, working at the Philips Company laboratory in the Netherlands. In 1948, thinking about the forces between molecules, he was led to a prediction so clean and so strange that it has become the signature effect of the quantum vacuum. Take two ordinary metal plates, he said, uncharged and flat, and bring them very close together facing each other. Empty space will push them together. To see why, go back to the vacuum's 0-point tremble in the electromagnetic field. That trembling can be thought of as a vast collection of tiny waves of every possible size filling all of space. Every wavelength that can exist is present in the vacuum, each carrying its small share of 0-point energy, the whole set humming together everywhere at once. Now slide two metal plates close together, and something changes in the gap between them. Metal plates constrain the electromagnetic field at their surfaces, so only certain waves can fit neatly in the narrow space between, those whose sizes match the gap. Waves too large to fit are shut out of the gap. Outside the plates, in the open space around them, waves of every size are still free to exist, the full unbroken set. So the region between the plates holds fewer kinds of vacuum waves than the region outside. That imbalance is the whole effect. With fewer waves pressing out from the inside than pressing in from the outside, the plates feel a net push inward, squeezed together by the fuller vacuum surrounding them. Nothing is pulling them. They are being pressed from without by the weight, so to speak, of all the vacuum waves that the gap between them cannot hold. Two neutral plates in the dark with no charge and no field applied drift toward each other, driven by the structure of empty space itself. This is the Casimir effect, and it is worth pausing on how bare it is. There is no electricity here, no magnetism switched on, no matter in the gap, no heat. There is only the vacuum, and the fact that placing two plates close together changes what the vacuum is allowed to do between them. The force is a direct mechanical consequence of the 0-point energy being real. If empty space truly held nothing, there would be no waves to exclude, no imbalance, and no push. The plates would sit still. That they move is the vacuum making itself felt. The force is real but faint, and it hides at everyday distances. It grows quickly as the plates come closer, and it only becomes noticeable when they are separated by less than the width of a hair, down near the scale where the exclusion of waves really begins to bite. At those tiny gaps, the push becomes strong enough that a careful experiment could hope to measure it, though in 1948 the measurement lay well beyond what anyone could do. Casimir had a prediction, elegant and exact, and for a long time it stood mostly as a beautiful piece of theory. Still, think about what he had claimed. Not that the vacuum shifts an atom's energy by a whisker, as in the Lamb shift, but that the vacuum can reach out and move solid metal, press two plates together with a force you could in principle weigh. It turned the restless vacuum from something felt inside atoms into something that acts on objects you could hold in your hand. The energy of empty space, if Casimir was right, had a mechanical grip on the ordinary world. The claim was bold enough that it demanded a direct test, plates brought close in a real laboratory, the force caught and measured against the prediction. That test would take about half a century to perform with real precision, and when it finally came, it confirmed that empty space does indeed push, exactly as Casimir's calculation said it would. The test finally came in 1997 at the University of Washington in Seattle, in the hands of a physicist named Steve Lamoreaux. Casimir's prediction had waited nearly 50 years, not because anyone doubted the mathematics, but because the force is so faint and the plates must be brought so close, held so steadily, that the measurements sat at the very edge of what instruments could do. Lamoreaux found a way to reach it. His challenge was mechanical before it was anything else. To feel the Casimir push, two surfaces must come within a fraction of the width of a human hair and stay there without touching, without tilting, without any stray charge or speck of dust ruining the reading. Keeping two flat plates perfectly parallel at such a gap is nearly impossible, since the smallest tilt spoils everything. So Lamoreaux made a clever change of shape. He used a flat plate facing a gently curved lens surface, a geometry that gives the same kind of force but sidesteps the need for perfect alignment. To measure the push itself, he hung one surface from a torsion pendulum, a delicate arm suspended by a fine fibre that twists when a sideways force acts on it. The Casimir force, tugging the surfaces together, would twist the fibre by a tiny angle. By watching that twist as he changed the gap between the surfaces, Lamoreaux could read off the strength of the force at each separation and compare it, point by point, against the curve Casimir's theory had drawn half a century before. The two matched. As the surfaces came closer, the measured force climbed just as the calculation said it should, following the predicted shape within a few percent. Empty space was indeed pushing by exactly the amount the zero-point energy required. The prediction that had lived so long only on paper was now a reading on an instrument, confirmed in a laboratory, as real as the weight of a coin in your hand. Others soon followed with sharper tools. A year later, Uma Mohideen and Anushri Roy at the University of California measured the same force using the fine tip of an atomic force microscope, a device built to feel forces between the smallest surfaces, and their agreement with theory was tighter still. Over the years, the Casimir force has been measured many times over, in different shapes and materials, and it holds up every time. It is now one of the sturdiest facts we have about the vacuum. Sit with what that means. Two ordinary pieces of metal, carrying no charge, sitting in the dark with nothing between them, drift together because empty space itself is not empty. The gap between them holds fewer of the vacuum's waves than the space outside, and that imbalance alone pushes them closer. Nothing in the older physics could produce such a force. It exists only because the quantum vacuum is a real structured thing, humming with a zero-point energy that leaves a mark on the everyday world of solid objects. The Casimir force also carries a warning that will matter later. It shows that the energy of the vacuum is not just a number in an equation safely ignored. It has physical consequences. It moves things. And if the vacuum's energy can push two plates together, then the total energy stored in all that empty space is a genuine physical quantity, one that ought to weigh something and act on the universe at large. Holding that thought will lead us in time to the strangest mismatch in all of physics. For now, we have seen the vacuum shift an atom's light and push on metal plates. It does something subtler too, something that changes the very charge of an electron depending on how closely you look. To see it, we return to the flicker of virtual particles and watch what that flicker does to a single electric charge sitting quietly in the void. Place a single electron alone in empty space and ask a simple question. How strong is its electric charge? The everyday answer is that it has one fixed value, the same whether you stand far off or leaning close. The vacuum makes the truth stranger than that, and the reason is the flicker of virtual pairs we met earlier. Around the lone electron, the vacuum is constantly producing brief pairs, a virtual electron and a virtual positron winking into being and vanishing again. In the fleeting moment they exist, the electron's charge acts on them. The pair carries opposite charges, so the electron pulls the positive member a little toward itself and pushes the negative member a little away. For that instant, the pair lines up, positive side facing the electron, negative side turned outward. Then it vanishes, and another pair forms and lines up the same way, and another, all through the space around the charge. The effect is a kind of screening. The layer of virtual pairs, always tilting so their positive sides face inward, wraps the electron in a faint fog of opposite charge. Seen from far away, through all that fog, the electron's charge looks partly cancelled, softened by the cloud of virtual pairs standing between it and you. What we normally call the electron's charge, the value measured at everyday distances, is this softened, screened figure, not the bare charge underneath. This screening of a charge by the vacuum's virtual pairs is called vacuum polarization, and it has a clear consequence. If you push in closer to the electron, past some of the screening fog, you see less of the cloud and more of the true charge. So the charge looks stronger the nearer you get, and weaker the farther away you stand. The electron's charge is not one fixed number after all. It grows as you approach, because you are pushing through the vacuum's screening layer toward the bare charge at the centre. An old and imperfect comparison is a lamp seen through mist. From far off, the mist scatters the light and the lamp looks dim. Walk toward it, leaving mist behind you, and it brightens, because less fog stands in the way. The electron is like that lamp, and the vacuum's virtual pairs are the mist. Where the comparison fails is telling. Real mist just sits in the air, a thing in its own right. The vacuum's fog is not a substance floating there. It is the response of empty space itself to the presence of the charge, a polarization of the void that appears only because the charge is there to stir it. This is not a fine point of theory that hides from view. Physicists measure it. In the great particle colliders, where electrons are smashed together at enormous energy, they meet each other very close indeed, deep inside the screening cloud. And there, the electron's charge is measurably stronger than the value we find in ordinary experiments at arm's length. The charge runs, as physicists say, growing with the energy of the collision, and it runs by exactly the amount vacuum polarization predicts. The screening fog of the void is real enough to change the numbers that come out of a collider, so the vacuum does not merely tremble and push. It acts as a medium, softening the charge of every particle in it, wrapping each one in a cloud of its own restlessness. The empty space around an electron is doing quiet work, shaping how strong that electron appears. And once we accept that the vacuum can hold a value that shapes the particles within it, we are ready for the deepest case of all, a field whose vacuum setting does not soften a property, but grants one, handing mass itself to the matter of the world. Some particles are heavy, and some are light, and for a long time no one could say why. An electron has a small mass. The particles that carry the weak nuclear force, called the W and Z bosons, are enormously heavy, each about 90 times the mass of a proton. The photon, the particle of light, has no mass at all, and so flies at the full speed of light forever. These differences seemed arbitrary, a list of numbers nature simply handed down without reason. In 1964, several physicists working separately found a way to explain them, and the clearest voice among them belonged to a quiet Englishman named Peter Higgs. The others, including Robert Brute and François Englert in Belgium, reached closely related ideas at nearly the same time. Their shared proposal was that the vacuum holds one more field, spread through all of space like the others, but with a strange and crucial difference. This field does not rest at zero in empty space. It rests at a value that is switched on, present everywhere, even in the emptiest void. This is the Higgs field, and the idea is that mass is not a property particles simply have on their own. Mass is something they acquire by wading through the Higgs field that fills all of space. A particle that interacts strongly with the field is slowed by it, hard to push, and that resistance to being pushed is exactly what we mean by mass. A particle that ignores the field, like the photon, feels no drag and stays massless. The heavy W and Z bosons are heavy because they couple tightly to the Higgs field. The electron is light because it couples weakly. Mass becomes a measure of how much each particle feels the field that soaks the vacuum. The often repeated comparison is a room full of people. An unknown guest crosses the empty room easily, quick and light. A famous one is swarmed, surrounded by a crowd that clings and slows every step, so the same walk takes far longer. The crowd gives the famous guest a kind of heaviness they did not have alone. The Higgs field is the crowd filling the room of space, and each particle's fame is how strongly it draws that crowd around itself. The comparison is loose, and it leaks in places, but it catches the core idea that mass comes from a thing pulling on you as you move through the vacuum. For decades, this was a beautiful guess with a heavy demand attached. If the Higgs field truly fills space, then plucking that field hard enough should produce its own ripple, its own particle, the Higgs boson. Finding that particle would show the field was real. But the Higgs boson was predicted to be very heavy and very short-lived, far beyond the reach of the machines of the 1960s and for long after. The idea waited, elegant and unproven, for almost 50 years. The wait ended in 2012. At the Large Hadron Collider near Geneva, the largest machine humans have ever built, two vast experiments smashed protons together at tremendous energy, sifting through the debris for the faint signature of the predicted particle. They found it, a new particle of just the right kind, at a mass a bit more than 125 times that of a proton. The Higgs boson was real, which meant the Higgs field was real, present in every corner of empty space. Peter Higgs and François Englert received the Nobel Prize the following year, nearly half a century after the prediction. So the vacuum holds a field that is switched on everywhere, and that field is the source of mass. But this raises a sharp question of its own. Why should a field settle at a value other than zero, when zero seems the natural place for anything to rest? The answer lies in a subtle and powerful idea called broken symmetry. Left to itself, a field wants to sit at its lowest energy, the bottom of whatever valley it finds. For most fields, that lowest point is at zero, the field's switched off, calm and flat. The Higgs field is different because the shape of its energy is different, and that shape is the key to why the vacuum came out the way it did. Picture the energy of the Higgs field as a landscape, with the height of the land standing for how much energy the field holds at each possible value. For an ordinary field, this landscape is a simple bowl, lowest in the middle, so the field rolls to the centre and rests at zero. The Higgs landscape is not a plain bowl. It is shaped more like the bottom of a wine bottle or a sombrero, with a raised bump in the very centre and a circular trough running around it at some distance out. The lowest energy is not at the centre anymore. It is down in the ring-shaped valley, away from zero. So the centre, the value of zero, is not the resting place. It is the top of a small hill. A field balanced there is like a ball perched on a dome, and the slightest nudge sends it rolling down into the surrounding trough, coming to rest at some value away from zero. That is where the Higgs field sits throughout the universe, down in the trough, switched on, holding the non-zero value that gives particles their mass. Empty space rests not at the peak in the middle, but in the valley around it. Here is the subtle part, the part that gives this its name. The landscape is perfectly round, symmetric, the trough equally low all the way around the circle. Before the field rolls, no direction around the ring is special, but the field cannot rest in the trough and stay in the centre at once. It has to pick one spot in the circular valley to settle into, one direction out of the many that were all equally available. The moment it does, the perfect roundness is broken. The underlying laws stayed symmetric, treating every direction alike, yet the actual state the field chose singled one out. This is called spontaneous symmetry breaking, a symmetry that is real in the laws but broken in the outcome. You see the same thing in a simpler setting. Balance a pencil perfectly on its point and every direction is alike, none preferred. Let go, and it must fall one way. It topples towards some particular direction, and now that direction is special, though nothing in the setup favoured it beforehand. The laws were even-handed. The result was not. The pencil had to choose, and in choosing it broke the symmetry it started with. For the Higgs field, this breaking is what fills the vacuum with a switched-on value and hands master matter. Early in the universe, when everything was extremely hot, the field is thought to have sat up on the central bump, symmetric, at zero, and every particle was massless and flew at light speed. As the universe cooled, the field rolled down off the bump into the trough, settling on its non-zero value, and in that moment particles gained their masses. The mass of the electron, of the quarks, of the heavy force carriers, all date from the instant the Higgs field fell into its valley and broke the symmetry. So the vacuum we live in bears the mark of an ancient choice, a field that rolled downhill long ago and has rested there ever since. We do not stand in a neutral, switched-off emptiness. We stand inside a field with a definite value, the same everywhere we can see, and that value shapes everything built from matter. It is worth stopping to feel where all of this has brought us, because the picture of empty space is now very far from the one we started with. Take a region of space and clear it of every particle, every atom, every scrap of light, and it is still not blank. The electromagnetic field runs through it, trembling with zero-point motion. Every other particle field is there too, humming at its own floor. And soaking all of it, switched on at a definite value, is the Higgs field, the same in this room, in the space between the stars, and in the vast dark between galaxies. We live inside that field the way a fish lives inside water, so completely surrounded by it that we never feel it as a thing apart. The Higgs field has no taste, no colour, no push you can sense directly. Yet without it, your body would fly apart into massless particles moving at the speed of a light, because the mass that holds you together, that makes matter slow and solid and able to gather into atoms, comes from the field's steady value everywhere. The solidity of the world is a gift of a vacuum that is switched on. This changes the meaning of the word emptiness in a deep way. When physicists say a region is empty, they no longer mean it contains nothing. They mean it holds no particles above the ground state, no ripples above the calm. But the calm itself is a rich, structured thing, a set of fields, each resting at its lowest allowed level, one of them resting not at zero but at a value that fills space with consequence. The emptiest possible space is still a place with definite properties, definite fields, a definite setting of the Higgs, and those settings could in principle have been otherwise. If the Higgs field had rolled into its valley at a different value, the masses of particles would be different, and the whole character of matter would shift. Make the field's value a little larger or smaller, and atoms might not form, stars might not burn, and the universe might hold nothing that could ever wonder about it. The particular value our vacuum settled on is one of the reasons the world is livable. That it came out fit for atoms and stars is either a deep necessity we do not yet understand, or a fact we have no full explanation for at all. This is the honest edge of our knowledge, and it is worth naming plainly. We know the Higgs field is real because we found its particle. We know it fills space and gives mass because the mathematics works and the numbers match. What we do not know is why its value is what it is, why the vacuum settled exactly where it did, rather than somewhere that would have made a barren universe. That question is open, and physicists do not agree on the answer. So we hold the vacuum now as a living state, full of fields, one of them switched on across the whole of space, shaping matter itself. The empty jar on the kitchen table, cleared of its air, is filled with all of this, whether we can feel it or not. Everything we have found so far has stayed within the world of particles and fields, the small-scale physics of matter and light. But there is a larger stage we have not yet brought in, the stage of gravity, of space and time bending under the weight of what fills them. If the vacuum holds energy, and we have seen many times that it does, then that energy should have weight, and weight bends space. The moment we let the vacuum's energy speak to gravity, we meet a puzzle far larger than any so far, one written into an equation Einstein set down, almost by accident. To bring gravity in, we need Einstein's greatest work, the theory of general relativity, finished in 1915, 10 years after he retired the ether. General relativity is our deepest account of gravity, and its central idea is that gravity is not a force reaching across space in the ordinary sense. It is the bending of space and time by whatever holds energy. Mass and energy curve the space around them, and other things move along that curve. The Earth circles the Sun because the Sun's mass bends the space nearby, and the Earth simply follows the bent path. The heart of the theory is an equation that ties the curving of space and time on one side to the energy and matter filling it on the other. Put energy in, and space curves in response. It is a precise and beautifully tested relationship, and it governs the whole universe, from the fall of an apple to the wheeling of galaxies. When Einstein first wrote it down, he expected it to describe a universe that was, on the larger scale, unchanging, neither growing nor shrinking, since that was what everyone assumed the cosmos to be. His own equation refused to give him that. When he worked out what it predicted for the universe as a whole, filled evenly with matter, it would not stay still. The gravity of all that matter pulled inward, so the whole universe should be contracting, collapsing slowly under its own weight. A static universe, the kind Einstein believed in, was not a solution his equation allowed. Something had to hold the matter apart against its own gravity, or the cosmos would fall in on itself. So in 1917, Einstein added a term to his equation by hand to fix the problem. He called it the cosmological constant, and its role was to supply a gentle outward push spread evenly through all of space, exactly balancing the inward pull of matter and holding the universe still. It was an extra piece with a clear job, a pressure built into space itself that worked against gravity. With it, his equation could describe the static, unchanging universe he expected to see. Now here is the quiet significance of that term, seen with modern eyes. The cosmological constant is in effect an energy belonging to empty space. It is a property of the vacuum, the same everywhere, present whether or not any matter is around. When Einstein added it, he did not think of it that way. He thought of it as a fix, a mathematical adjustment to save a static universe. But in the language we have been building, the cosmological constant is precisely a vacuum energy carried by space itself, written directly into the law of gravity. That is the deep link this chapter exists to draw. Everything we found in the small world, the zero-point tremble, the flicker of virtual pairs, the switched-on Higgs field, gives empty space a store of energy. And general relativity says energy bends space and time. So the energy of the vacuum cannot be a private matter of particle physics, tucked away and harmless. It must speak to gravity. It must, through Einstein's equation, shape the universe at the larger scale. The cosmological constant is the place where the vacuum's energy and the bending of the cosmos meet. Einstein had introduced this term for his own reasons, to prop up a still universe. Within little more than a decade, the heavens themselves would show that the universe is not still at all, and Einstein would come to regret the whole addition, calling it, by one famous account, the worst mistake of his life. Yet the term he tried to erase would return, unbidden, to sit at the centre of the greatest puzzle the vacuum has ever posed. The news that undid Einstein's static universe came from the American astronomer Edwin Hubble, working through the 1920s with the Great Telescope on Mount Wilson in California. Hubble was measuring the distances to faint smudges of light called nebulae, and proving that many of them were whole galaxies far beyond our own, islands of stars scattered through a universe vastly larger than anyone had pictured. Then he measured how they were moving, and found something no static universe could survive. The galaxies were nearly all moving away from us. More than that, the farther a galaxy was, the faster it was receding, in a steady proportion Hubble laid out clearly by 1929. The distant ones fled quickest, the nearer ones more slowly, in a pattern that pointed to one plain conclusion. The universe was not sitting still. It was expanding, every part drawing away from every other, like a loaf of raisin bread rising in an oven, each raisin carried from its neighbours as the whole dough swells. An expanding universe was exactly what Einstein's equation had wanted to give him before he forced it to hold still. Had he trusted the raw mathematics, he might have predicted the expansion years before Hubble saw it. One of the great missed predictions in the history of science. Instead, he had added the cosmological constant to prevent the very motion that turned out to be real. With the universe now plainly expanding, the constant had no job to do. There was no need for a term to hold the cosmos static, because the cosmos was not static. So Einstein dropped it. He removed the cosmological constant from his equation and let general relativity describe an expanding universe on its own, which it did cleanly. According to a much-repeated account from the physicist George Gamow, Einstein later called the cosmological constant the biggest blunder of his life. Whether he used exactly those words is uncertain, and the story may have grown in the telling. But the sentiment fits what he did. He had marred his most beautiful theory with an extra term to chase a picture of the universe that proved false, and once the truth was known, he wished the term gone. For most of the 20th century, that is where matters stood. The cosmological constant was treated as a mistake, set to zero, left out of the working equations. The universe expanded because it had begun in a hot, dense state and was still flying apart from that beginning, and the expansion was expected to slow over time, dragged on by the gravity of all the matter within it. Every galaxy pulls on every other, so the sensible guess was that the expansion should be gradually breaking, like a ball thrown upward losing speed as it climbs. The only open question seemed to be how much the expansion was slowing, and whether it would slow enough to halt and reverse someday, or coast outward forever at an ever gentler pace. Either way, the pull of matter should be putting on the brakes. The cosmological constant, Einstein's discarded term, played no part in the standard picture. It was a historical curiosity, a wrong turn that a great man had taken and corrected. That settled state of affairs lasted until the very end of the century, when two teams of astronomers set out to measure the slowing of the expansion precisely, expecting only to pin down how fast the brakes were being applied. They looked deep into space, at exploding stars in distant galaxies, to catch the universe in the act of decelerating. What they found instead was the opposite of braking, and it would drag Einstein's abandoned term back into the heart of physics. The two teams raced each other through the 1990s, both hunting the same faint signals. One was the Supernova Cosmology Project, led by Saul Perlmutter at the Lawrence Berkeley Laboratory in California. The other was the High-z Supernova Search Team, led by Brian Schmidt, and including Adam Rees. Both were after a particular kind of exploding star, and both wanted to measure how the expansion of the universe had changed over billions of years. Their tool was a special type of stellar explosion called a Type 1 supernova. These happen when a dense stellar ember, a white dwarf, gathers too much matter and detonates, and the useful thing about them is that they explode with very nearly the same true brightness every time. That makes them standard candles. If you know how bright a thing truly is, and you measure how bright it looks from Earth, you can work out how far away it is, since distant things look fainter in a known way. So each of these supernovae was a distance marker scattered across the depths of space. There was a second gift hidden in the light. As the universe expands, it stretches the light travelling through it, shifting its colour toward the red, and the amount of that redshift tells you how much the universe has grown since the light set out. So for each supernova, the teams could find two things at once: how far away it was from its brightness, and how much the universe had expanded since the explosion from its redshift. Put many of them together, near and far, and you can trace how the expansion rate has changed over cosmic history. They expected to see the expansion slowing. The distant supernovae, whose light had travelled for billions of years, should show a universe that was expanding faster back then and had been breaking ever since, dragged on by the gravity of its matter. The measurements would reveal how hard the brakes were pressed. Both teams gathered their supernovae, measured brightness and redshift with great care, and worked out what the numbers said about the changing expansion. The numbers said the expansion was speeding up. The distant supernovae were fainter than they should have been if the universe had merely been coasting or slowing. They were farther away than a decelerating universe could place them, which meant the expansion had not been breaking at all over the last several billion years. It had been accelerating, each galaxy racing away from the others faster as time went on, not slower. Both teams reached the same startling result at nearly the same time, around 1998, and their agreement made it hard to dismiss. This was the reverse of every expectation. Gravity pulls matter together, so the natural thing for an expanding universe full of matter is to slow down. For it to speed up, something must be pushing outward, some form of energy spread through space with a kind of built-in pressure that drives the expansion faster and faster. The pull of matter was there, but it was being overwhelmed by a push no one had ordered, a push coming from empty space on the largest scale. The discovery was so significant that the leaders of both teams, Perlmutter, Schmidt and Rees, shared the Nobel Prize in 2011. They had found that the universe is not merely expanding but expanding ever faster, driven by something unseen, and the simplest way to describe that outward push, in the mathematics of general relativity, was a term Einstein had written down 80 years before and then thrown away. The cosmological constant was back, and it now stood for a real energy in the vacuum, pushing the whole universe apart. The unseen push needed a name, and the one that stuck is dark energy. It was coined in the late 1990s by the cosmologist Michael Turner, and the word dark is honest, marking how little we understand it. Dark energy is the name for whatever is causing the expansion of the universe to accelerate, the outward pressure filling all of space. Naming it did not explain it. It gave physicists a shared word for a mystery they had just been forced to accept. The simplest candidate for dark energy is exactly the vacuum energy we have been building toward, energy belonging to empty space itself. If every region of space carries a small, fixed amount of energy, the same everywhere and unchanging as the universe expands, then that energy behaves in Einstein's equation just like his cosmological constant. It pushes outward, evenly, everywhere, and it drives the expansion faster over time. Read this way: dark energy is the energy of the vacuum, and the accelerating universe is the vacuum's energy made visible on the grandest scale. There is a feature of this energy that makes it strange and powerful. Ordinary matter thins out as the universe expands, its density dropping as the same amount of stuff spreads through a larger volume. Vacuum energy does not thin out. It is a property of space itself, so every new stretch of space that the expansion creates comes with its own full share of the energy. The density stays constant no matter how much the universe grows. This means that as the universe gets larger, matter grows ever more dilute while vacuum energy holds steady, so the vacuum's push comes to dominate more and more, and the acceleration strengthens with time. When astronomers add up the contents of the universe, dark energy turns out to be the largest part by far. Roughly 7/10 of everything, of all the energy in the cosmos, is this dark energy of empty space. Ordinary matter, the stuff of stars and planets and people, is only a few percent. The rest is another mystery, called dark matter, which is unseen but at least pulls inward like normal matter does. Dark energy stands apart, pushing outward, and it outweighs all the matter, dark and ordinary together. The universe, by the numbers, is mostly the energy of its own empty space. Return for a moment to the empty jar on the kitchen table. We have seen its emptiness fill with fields, with zero-point motion, with the switched-on Higgs. Now we can say something larger. That same vacuum, multiplied across the whole universe, carries an energy that is steering the fate of the cosmos, driving every distant galaxy away from every other, faster with each passing age. The leftover in the jar and the force reshaping the heavens are, in the simplest reading, the same thing seen at two vastly different scales. This should feel like a triumph, and in one sense it is. The vacuum energy we found in the small world seems to show up again in the sky as the dark energy accelerating the universe. The two might be one and the same, the theory of the very small meeting the observation of the very large. It is the kind of unity physicists live for, a single idea tying the jar to the cosmos. But when physicists tried to check the match, to calculate how much energy the vacuum should hold, and compare it to how much dark energy the sky actually shows, the two numbers did not agree. They missed by so vast a margin that the mismatch has become famous as the worst prediction in the history of physics, a gap so enormous it strains the mind to hold it. Here is the calculation that goes wrong. Quantum field theory says the vacuum is full of zero-point energy, every field contributing its share of restless activity at every point in space. In principle, you can add all of it up and work out how much energy empty space should contain, and then, through Einstein's equation, how strongly that energy should push the universe apart. Physicists did the sum. Then they compared it to the actual push, the dark energy that the supernovae revealed. The two numbers should have been close if the vacuum energy of particle physics is what drives the accelerating sky. They were not close. The amount of energy that quantum theory predicts for the vacuum is vastly, almost unimaginably larger than the amount the universe actually shows. The gap is not a factor of 10, or 1,000, or even a billion. Written out, the theoretical value overshoots the observed one by a factor, with something like 120 zeros after it. It is difficult to convey how large that mismatch is. If you shrank the entire observable universe down to compare it against a single atom, you would still not span a gap of that size. It is the largest disagreement between theory and measurement anywhere in science. This is the vacuum catastrophe, sometimes called the cosmological constant problem, and it is worth being clear about exactly what is broken. It is not that we see no dark energy, and theory predicts some. We do see dark energy, a real and measured push. The problem is the amount. Our best theory of the vacuum, the same quantum field theory that nails the Lamb shift and the Casimir force to many decimal places, predicts a vacuum energy so colossal that if it were true, the universe would have been torn apart in its first instant, ripped so violently that no galaxy, no star, no atom could ever have formed. A universe with that much vacuum energy would be uninhabitable, expanding so fast that nothing could hold together. So the very theory that succeeds so brilliantly in the small world fails, more badly than any theory has ever failed, when asked how much its vacuum energy should weigh. Something is deeply wrong with our understanding, right at the point where the physics of particles meets the physics of gravity. Either the vacuum energy is somehow cancelled almost perfectly, down to that 120th decimal place, by some effect we have not found, or the whole way we are adding it up is mistaken, or dark energy is something other than simple vacuum energy after all. The strangest part is how nearly the cancellation must work, if cancellation is the answer. To bring that enormous predicted energy down to the tiny value we observe, some unknown mechanism would have to trim it away almost exactly, leaving only the faintest sliver behind. Not zero, because there is a little dark energy, but so close to zero on the scale of the prediction that the precision required looks absurd. It is as if 120 digits all cancelled, and the 121st did not, for reasons no one can name. This is not a small crack at the edge of physics. It sits at the centre, where our two greatest theories, quantum field theory and general relativity, are supposed to meet. Both are magnificently successful on their own. Put together, on the question of what the vacuum weighs, they produce the worst answer in the history of the subject. The vacuum, which we have followed from an empty jar all the way to the accelerating cosmos, hands us a mystery that no one has solved. Faced with a mismatch that large, physicists have not stayed silent, though no one can claim a settled answer. The honest state of things is that the vacuum catastrophe is unsolved, one of the deepest open problems in all of science. Still, There are lines of thought, and they are worth walking through calmly because they show how physics behaves when it meets a wall it cannot yet climb. One idea is that some symmetry, some deep balance in nature, forces the huge positive and negative contributions to the vacuum energy to cancel almost perfectly. In this hope, the reason the vacuum energy is so tiny is that nearly everything cancels by a rule we have not yet found, leaving only a small remainder. Physicists have searched hard for such a symmetry. One candidate, called supersymmetry, would pair up particles in a way that cancels much of the vacuum energy neatly. But if that symmetry exists in nature, it is broken, and a broken version does not cancel cleanly enough to close the gap. The cancellation idea is attractive and so far incomplete. A very different line of thought accepts the small value without deriving it, and asks instead why we find ourselves in a universe where it is small. Suppose there are many regions, or many universes, with the vacuum energy taking different values across them, most of them enormous. In almost all of those regions, the energy would be so large that the expansion would prevent galaxies, stars, and life from ever forming. Only in the rare regions where the energy happened to be small could observers arise to measure it. So of course we find a small value, because a large one would have left no one to find anything. This is called anthropic reasoning, and the physicist Steven Weinberg used it in 1987 to argue that the vacuum energy, if it were not zero, should be small, roughly in the range later observed. Anthropic arguments make many physicists uneasy, and it is fair to say why. They can feel like giving up on a real explanation, settling for the observation that we could only exist where the number is livable. If taken too far, such reasoning explains everything and predicts nothing. Yet Weinberg's estimate was made before the acceleration was discovered, and it landed close to the value that later turned up, which is not nothing. Whether that is insight or coincidence is still argued. The truth is that these ideas remain guesses, and the field has not converged on any of them. Some physicists suspect the whole framework is missing a piece, that we are adding up the vacuum energy in a way that will look naive once we understand gravity and the quantum world together in a single theory. That deeper theory, a full marriage of general relativity and quantum mechanics, does not yet exist in finished form, and the vacuum catastrophe may be one of its loudest demands, a sign pointing toward the physics we have not yet reached. So we live with the gap, honestly, without pretending it is closed. The vacuum holds an energy that pushes the universe apart. We have measured that push, and our best theory of the vacuum cannot say why the push is as gentle as it is rather than ruinously strong. It is a humbling place to stand, and also a hopeful one, because a mismatch this sharp is exactly the kind of thing that has forced physics forward before. The failures of the ether led to relativity. This failure, sitting between the very small and the very large, may lead somewhere just as new. While that puzzle waits, the same idea of a vacuum energy that pushes space outward turns out to solve a different problem beautifully, back at the very beginning of the universe, in its first fraction of a second. Rewind the expanding universe, running it backward, and everything draws closer together, hotter and denser, until you reach the earliest moments after the beginning we call the Big Bang. The standard picture of that hot, dense start explained a great deal, but it left a few stubborn puzzles that would not resolve. In 1980, a young American physicist named Alan Guth found a way to answer them all at once, with an idea that leans directly on a vacuum-like energy. One puzzle was that the universe looks remarkably the same in every direction, even in regions so far apart that they should never have been in contact. Look at opposite sides of the sky, and they share the same temperature to great precision, yet in the standard story there was never time for them to reach that balance. No way for one side to have influenced the other. Another puzzle was that space appears almost perfectly flat, finely balanced, when the natural expectation was for it to be strongly curved. These looked like coincidences too precise to be accidents, and they cried out for a cause. Guth's idea, which he called inflation, was that the very early universe went through a brief burst of staggeringly fast expansion doubling in size again and again in a tiny fraction of a second, growing by an enormous factor before settling into the steadier expansion we see today. What could drive such a burst? A vacuum energy. Guth proposed that the early universe was briefly caught in a state with a very high vacuum energy, a temporary setting of the fields that carried a large outward push, and that push blew the universe up at a furious rate. This vacuum-driven expansion cleared up the puzzles neatly. The regions that look alike were, before inflation, packed close enough to reach a common temperature, and inflation then stretched them far apart while preserving their sameness, which is why opposite sides of the sky still match, and the ferocious stretching flattened space the way blowing up a balloon flattens any small patch of its surface, driving the curvature towards zero and explaining why space looks so flat. One idea, a burst of vacuum-like energy, accounted for several separate mysteries at once. There is a further gift in inflation, and it ties straight back to the restless vacuum. During that rapid expansion, the ordinary quantum fluctuations of the vacuum, the same flicker of the fields we have followed throughout, were stretched along with everything else, blown up from tiny quantum ripples to enormous scales across the sky. Those stretched fluctuations became slight variations in the density of the early universe, denser here, thinner there, and those variations were the seeds. Over billions of years, gravity pulled matter into the denser spots, and they grew into galaxies and clusters of galaxies. The largest structures in the universe may be quantum vacuum flickers, magnified by inflation to span the heavens. Inflation is widely accepted among physicists because it explains so much, and because its predictions, especially the pattern of those density variations, match what we see in the faint afterglow of the Big Bang with real precision. It is not fully settled, and the exact field that drove it remains unknown, so honesty requires marking it as our best framework rather than a closed case. But its core lesson stands. A vacuum energy, high and temporary, shaped the newborn universe and sowed the seeds of everything within it. That the early universe could sit in a state of high vacuum energy, only to leave it later, raises a quiet and unsettling question about our own vacuum. If the vacuum once held a different higher value, and then dropped to a lower one, how do we know our present vacuum is truly the lowest it can reach? The question is sharper than it first sounds, and it turns on the difference between the lowest place around and the lowest place there is. Think again of the Higgs field resting in its trough, the wine bottle valley around the central bump. We pictured that trough as the bottom, the field's true resting place. But suppose the real energy landscape is more complicated than a single valley. Suppose that beyond the trough we sit in, past a ridge, there lies another valley, deeper still, a place of even lower energy that the field has not reached. If that were so, our vacuum would not be the true bottom. It would be a false vacuum, a resting place that looks stable, that has held steady for billions of years, but that is not the lowest state available. The field sits in a hollow partway down the mountain, comfortable, seemingly at rest, while somewhere below there is a deeper hollow it could in principle fall into. A false vacuum is a valley that is not the deepest valley, a calm that is not the final calm. Whether our vacuum is true or false depends on the exact shape of the field's energy landscape, and in particular on the Higgs field and the masses tied to it. Here the real measurements become tense. The mass of the Higgs boson, found at the Large Hadron Collider, and the mass of the top quark, the heaviest known particle, feed into a calculation of the landscape's shape. When physicists run that calculation with the measured values, the answer comes out close to a knife's edge. Our vacuum appears to sit right near the boundary between being truly stable and being only metastable, a false vacuum that could, given enough time, decay. The result is uncertain, and it depends sensitively on numbers we do not yet know precisely enough, especially the top quark's mass. Small changes in the inputs tip the answer from stable to metastable and back, so no one can say for certain which case we are in. But the striking thing is that the question is even close. Our universe seems to sit near the edge, not comfortably deep in a stable valley, and physicists do not fully understand why it should land in such a finely balanced spot. If our vacuum is metastable, a false vacuum, then it is not eternal. It has an enormous lifetime, far longer than the current age of the universe, so there is no cause for alarm about tomorrow or the next billion years. But over unimaginably long spans, a false vacuum can decay, slipping at last into the deeper valley below. The calculations that place us near the edge also suggest that, if we are metastable, the time before any such decay is likely to be staggeringly long, far exceeding the age of the cosmos so far. Still, the mere possibility reshapes how we think about empty space one final time. Through all these chapters, we have treated the vacuum as the ground, the floor, the bottom rung. Now, we face the chance that our floor is not the true floor, that beneath the emptiness we know there could be a lower emptiness, more stable, more final, that our world has simply never reached. The stage the universe rests on might have a trapdoor, and if a false vacuum ever did decay, the manner of it would be one of the strangest events physics can describe, a change that begins in a single point and spreads outward at nearly the speed of light. Here is how the decay of a false vacuum would unfold, according to the physics of such things, worked out by Sidney Coleman and others in the 1970s. Somewhere in space, by pure quantum chance, a tiny region of the field would slip over the ridge and settle into the deeper valley, the true vacuum. This would form a bubble, a small pocket of true vacuum surrounded by the false vacuum we live in. And because the inside of the bubble sits at lower energy, the bubble would be favoured to grow it would, and fast. The wall of the bubble, the boundary between the old vacuum and the new, would sweep outward, accelerating until it moved at nearly the speed of light. Inside the expanding bubble, the fields would rest at their new, lower values, and the laws of physics there could be different from ours. The masses of particles, the strengths of forces, the very possibility of atoms, all could change across that wall. Whatever lay in the bubble's path would meet those new laws as the wall reached it. Because the wall travels so close to the speed of light, there would be almost no warning. The light announcing the bubble's approach would arrive only just before the wall itself, so a region would have essentially no time to see it coming. One moment the ordinary vacuum, the next the wall sweeping through, and behind it a patch of universe running on different rules, in which the structures of our world, atoms and molecules and everything built from them, might simply not be able to exist. This is vacuum decay, sometimes called false vacuum decay, and it is about as complete a transformation as physics allows. It is important to hold this idea at the right distance, calmly and honestly, because it is easy to let it loom too large. First, we do not know that our vacuum is false. The measurements place us near the edge between stable and metastable, but they do not settle which side we're on. Second, even if our vacuum is metastable, the expected time before any such bubble forms is astronomically long, far longer than the age of the universe, so long that the practical chance of it happening in any span we care about is essentially nothing. This is not a danger to lose sleep over. It is a consequence to understand. What makes it worth understanding is what it reveals about the vacuum's character. The very fact that vacuum decay is a coherent idea, that physicists can calculate how such a bubble would form and spread, tells us the vacuum is a real physical state that could in principle be otherwise. A true nothing could not decay, for there would be nothing to change. The vacuum can be imagined to fall to a lower state precisely because it is a something, a configuration of fields resting at particular values that might not be the deepest ones available. So the possibility of vacuum decay is not really a story about catastrophe. It is the sharpest possible statement of everything we have learned. Empty space is a state, with a definite energy and a definite setting of its fields, and like any state it can be asked whether it is truly the lowest or only a resting place along the way. That the question has meaning is the final proof that the vacuum is not nothing. There is one last place to see the vacuum reveal itself, and it is the most dramatic of all at the edge of a black hole, where the ordinary flicker of empty space is torn in two and made to shine. A black hole is a region where gravity is so strong that nothing, not even light, can escape from within a certain boundary, called the event horizon. Cross that horizon, and there is no return, no signal that can climb back out. By the ordinary rules of gravity, a black hole should be utterly black, emitting nothing at all, a perfect trap that only grows as it swallows more and lets nothing go. For a long time, that was the accepted picture. In 1974, the British physicist Stephen Hawking showed it was not quite true, and he did it by taking the quantum vacuum seriously right at the edge of the horizon. Recall the vacuum's restless flicker, the virtual pairs of particles constantly forming and vanishing everywhere in empty space, a particle and its antiparticle appearing together and annihilating back almost at once. This goes on at the event horizon of a black hole just as it does anywhere else, but at the horizon, the pair can meet a fate it never meets in ordinary space. Now and then, as a virtual pair forms right at the boundary, the two members can be split apart before they annihilate. One falls across the horizon, lost into the black hole forever, while the other escapes outward, away from the black hole into the space beyond. Separated, they can no longer meet and vanish. The escaping member is left behind as a real particle, carrying real energy away from the black hole, born from the vacuum's flicker at the very edge of no return. To a distant observer, the black hole appears to glow faintly, giving off a thin stream of these escaped particles. This faint glow is called Hawking radiation, and it changed our understanding of black holes completely. A black hole is not perfectly black after all. It shines, ever so dimly, with radiation drawn from the vacuum at its horizon. And the energy carried away by that radiation has to come from somewhere. It comes from the black hole itself, which loses a little mass each time a particle escapes. Slowly, over time, a black hole radiating in this way shrinks. Given long enough, vastly long for any large black hole, it could evaporate away entirely, undone at last by the restlessness of empty space. The rate is achingly slow for the black holes we know. A black hole the mass of the Sun would take unimaginably longer than the present age of the universe to evaporate, its glow far too faint to detect against the background of the sky. Smaller black holes would shine brighter and vanish faster, but none small enough has yet been found. So Hawking radiation has not been observed directly from a real black hole. It rests on solid theory, on bringing the quantum vacuum together with gravity, and it is widely accepted, though a direct measurement is still beyond us. What matters for our story is where the glow comes from. It is the vacuum again, the same flicker of virtual pairs we first met as a quiet, churning in empty space, now dramatized at the edge of a black hole into a stream of real, escaping light. The event horizon takes the vacuum's fleeting pairs and makes them permanent, turning the restlessness of the void into radiation that carries energy across the universe. The emptiest, most complete void imaginable, the inside of a black hole's grip, is ringed by a vacuum that shines. From an empty jar on a kitchen table to the glow at the rim of a black hole, the vacuum has shown itself again and again to be a something. It remains only to gather what we have found and return to the box we started with. So let us go back to the beginning, to the clean glass jar on the kitchen table, its lid screwed down tight. We pumped out the air, the crowd of molecules, and asked what was left. We can answer that question now, honestly and fully, and the answer is nothing like the simple emptiness we started with. Take everything out of the box, every atom, every particle, every scrap of light, cool it to the coldest temperature that nature allows, and here is what remains. The electromagnetic field still runs through it, trembling with a 0-point motion it can never lose. Every other field is there too, each humming at its lowest allowed level. Virtual pairs flicker in and out across every point, a constant quiet churning that no chilling can still. The Higgs field soaks the whole of it, switched on at a value fixed long ago, handing mass to any matter that might enter. And spread through it all is a faint energy that, on the scale of the universe, pushes the galaxies apart. The box is not empty. It is full of the deepest structure the universe has. This is the plain answer to the title's question. What empty space is hiding inside is not a lack but a state, the ground state of all the fields of nature, the floor the whole universe rests on. We call it the vacuum, and we have followed it from Torricelli's tube of mercury, through the ether that failed and the relativity that replaced it, into the quantum fields and their restless flicker, out to the accelerating sky and the puzzle of dark energy, and down to the edge of a black hole. At every step it refused to be nothing. Some of what we found is settled beyond real doubt. The 0-point energy is real, measured in the Casimir force. The vacuum's flicker is real, measured in the Lamb shift and in the running of the electron's charge. The Higgs field is real, its particle found. These are not stories. They are facts, checked to many decimal places, woven into the most precisely tested theories we have. And some of what we found is honestly unsettled, and it is worth ending on that edge rather than papering over it. We do not know why the vacuum energy is as small as it is, and the mismatch between prediction and measurement is the worst in the history of physics. We do not know for certain whether our vacuum is the true lowest or only a resting place. We do not fully understand how the physics of the very small, the quantum vacuum, joins with the physics of the very large, the bending of space and time. The vacuum sits exactly where our two greatest theories meet, and where they meet, they do not yet agree. That unfinished place is not a failure to hide. It is where the next physics will come from. Here is the thought to carry away from these 2 hours. The emptiness you pictured at the start, the plain gap between your fingers and the screen, is not a blank waiting to be filled. It is already full, trembling with fields, shaped by an ancient choice of the Higgs, faintly pushing the whole universe apart. You're not a small solid thing moving through a void. You're a set of ripples in fields that fill all of space, standing on the same ground state as every star, made of the same restless vacuum that shines at the edge of a black hole. The box is never empty. It never was. And that quiet, humming fullness, hiding in every gap you have ever looked through, may be the largest and strangest thing there is.